All right, so we have one last thing in chapter 20 that we need to knock out before we truly invest in chapter 21. And it's a little bit out of place uh, in the book. Like they have a section in chapter 20 in the book on alternating current or AC. And it seems weird to put that there because later on in chapter 23, they actually talk about alternating current or AC circuits. So you'd think that they would put that section in chapter 23 with everything else. Because we can't understand alternating current until we get a bit more information about magnetic fields, which happens in chapter 22. But they do at least introduce the concept of alternating current. And a lot of times I just kick this topic down the road until chapter 23 and address it there. But I can't really do that because I put an alternating current problem on your homework. So I should at least do what the book does and introduce the concept of alternating current right now, but we're not going to do a whole lot with it until chapter 23. So let's see if we can't make sense of alternating current and some of the terminology that gets used in reference to it. So far we've been referring to what we call DC circuits, where DC, of course, stands for direct current. And in a direct current circuit, what's going to happen is you've got a battery connected to something. I'm going to put a resistor here, but it could be anything. And what's going to happen is the nature of that battery is such that you've got a positive terminal, you've got a negative terminal. The voltage between those two terminals is always the same. Maybe it's like a Duracell battery. It's always 1.5 volts from one side of the battery to the other. A 9-volt battery, it's always 9 volts all the time. So that voltage is always constant and stays the same. And so when you hook that circuit up and current is going to start to flow, well, since the electric field always points from the high voltage to the low voltage, the current is always going to flow in the direction of high to low. So what's going to happen is you're always going to have current flowing out of your positive terminal, going through your circuit and coming back into your negative terminal. And that never changes. So in a direct current circuit, your current is constant, right? It doesn't increase or decrease. It's the same over time, or at least in the same direction over time, even if it's not the same value continuously. We'll see some examples later today where we have a DC circuit and the current's always in the same direction, but sometimes it's big and sometimes it's small. But in a DC circuit, the direction of the current is obvious. It's always going to be in the same direction. However, there's another way to generate currents, right? There's another way to create current. And the kind of current that it creates is something called alternating current. And that, of course, is AC. And what's going to happen in AC is we're going to generate the voltages a different way. Rather than using a battery, which is often generated by a chemical cell where you have, a positive terminal, a negative terminal, you're going to use another technique. And we'll deal with what that technique is in a couple chapters. Right now, let's just sort of leave it at that and say that we have a thing that creates a voltage, but that voltage isn't constant in the same way that a direct current battery is. it does instead create a voltage that varies with time. So imagine that this graph represents my voltage. In an AC circuit, what's going to happen is my voltage is sinusoidal. So it's going to look like a sine wave. And it's going to oscillate from being large and positive. I'm going to call this V naught. So sometimes it's large and positive, but then other times it's momentarily, just for a split second, the same as zero. And then later on again, it'll be as low as negative V naught. So it can actually switch from being forwards to backwards, and it goes back and forth, back and forth. That's why they call it alternating. So here your voltage would look like something like this. Where V naught is my maximum amplitude of my voltage. And omega is a number called the angular frequency. We saw this sort of stuff last semester when we did oscillations. So the angular frequency is basically is controlling how close together these peaks are. When omega gets big, then what's going to happen is these peaks get really, really close together. And when omega gets small, these peaks get really, really far apart. So essentially what's happening is by changing omega, you're changing how long you have to wait before the current gets all the way back around to its original value. It repeats more frequently at higher values of omega, and it repeats less frequently as omega gets smaller and smaller and smaller. If omega drops to zero, basically this turns into DC. And of course, the angular frequency is 2 pi times the regular frequency. Again, hopefully this looks familiar from back when we did oscillations last semester. It's the same notation. Where F is called the frequency. And you can think of F as just the number of times that this pattern repeats per second. It's measured in hertz. Now, it turns out that the vast majority of the household circuits that get used in the United States and everywhere else for that matter are alternating current. So if you plug something into the wall, you're using AC electricity. And in fact, the frequency of the power in your wall sockets right now is 60 hertz. That's the standard here in the United States. What that means is that the current is switching direction, going positive to negative and positive to negative. It's making that switch 60 times every second. So it's remarkably rapid in its switching. If you were to look at an AC circuit, what would happen is the current would switch every time the voltage switched. So when the voltage is big and negative, the current wouldn't be forward anymore. It would turn around and go backwards. And so if you could actually see the electrons inside the wire, rather than having them go all the way around the circuit, they actually never make it around at all. They just kind of jiggle forward, backward, forward, backward, forward, backward, forward, backward. But what's going to happen is that motion of those electrons is still enough to deliver power to whatever your resistances are. So if you got a light bulb and it's running on AC power, that light bulb still lights up. It's going to be lit up whether the current's going forward or backward, it doesn't matter. And so a great number of our devices run on AC power. Now, things that run on DC power tend to be things that run on batteries. Batteries are DC. but most of your wall sockets are AC. And in fact, many of your devices will be designed to run on DC, but get powered by AC. Case in point, I've got my Surface right now that I'm doing this video on. It's connected to the wall outlet. However, if your computer, your laptop, your iPad, or whatever, they're usually designed to run with DC. They have a DC battery that you charge up, and yet I charge that DC battery up by plugging it into the wall. And in fact, here's the cord for my Surface, and you'll notice this little boxy thing here. What this little boxy thing does is it's called a transformer, and it's got two things. It's a transformer and a rectifier. And what a transformer does is it converts the voltage at the wall from whatever the wall value is, which in this case is 120 volts, down to whatever the input of my Surface is, which is probably 12 volts. Probably says it on here somewhere. I'm going to guess 12. So it changes the voltage. That's what a transformer does. We'll learn how they work in chapter 23, so don't worry about it right now. A rectifier converts AC into DC, because what's going to happen is inside my rectifier, every time the current tries to go negative or the voltage tries to go negative, it won't let it. So it'll be like, I'm going positive, 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 positive. I want to be negative. Nope. Positive, 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 positive. I want to be negative. Nope. And so now the current only ever goes one direction, because all the places where it tried to go negative, the rectifier won't let it. So if you look at your charging cord for your computer or whatever, those little boxy things, that's usually the thing that's converting the alternating current in your wall into the direct current that your computer needs to charge up. So that's why you've got those big knobby things. So when we talk about alternating current, we run into a problem, right? If I say, hey, what's the voltage for this DC circuit? And you tell me, well, Tom, that's a 12-volt battery. Well, that voltage source is 12 volts. 2 seconds from now, it's still going to be 12 volts. It's pretty obvious that I've got 12 volts of battery power. If I ask you what the current is, well, you take the 12 volts, you divide it by whatever the resistance is, and you tell me, oh, it's, blah, blah, blah amps. But 2 seconds from now, how many amps am I going to have? The same number. So in a DC circuit, all these values, like the current and the voltage, they're constant, they're not changing. But if I'm dealing with alternating current and, I ask you, hey, what's the voltage in that alternating current circuit? What are you going to tell me? Because what's going to happen is the voltage keeps changing. Sometimes the voltage in that AC circuit is 0. But a split second later, it's some big number. And a split second after that, it's a little bit smaller, but still positive. And a split second after that, it's 0. A split second after that, it's negative something. So it has this whole range of different values that it takes. So I can't just say, oh, it's 12 volts, because it's only 12 volts for a split second, and then a split second later, it's something different. So it's really hard to talk about an AC circuit because everything keeps changing unless we adopt some sort of nomenclature for discussing it. So in order for us to talk about this value for the voltage that keeps changing and to assign one number to that voltage, the easiest thing to do would be to take an average, right? That's often what you do when you have a whole range of numbers, but you want to express them as one single number. You take the average of all the numbers. But a regular average isn't going to cut it for us today. To see why, think about how you would do an average, right? If I'm taking an average over time of all these values, typically what you would do is you'd add up all your numbers and then divide by how many numbers you've got. But the problem is, if I try that approach for this sine wave kind of deal, what's going to happen is for every time I have, imagine this V naught is like 10, right? Every time I have positive 10, there's going to be another moment down here where it's negative 10, right? Every time I have a moment when it's positive 5, there's going to be another moment when it's negative 5. And what's going to happen is, if I try to average all those out, well, I'm going to get 0. Because for every positive, I have a negative canceling it out. The average voltage in an AC circuit is just flat out 0. But that doesn't really help me very much, because even though the average voltage is 0, I'm still getting current flowing one direction, lighting my light up, current flowing the other direction, lighting my light up. So I want to be able to distinguish between having an AC voltage like this, where it's positive and negative, and I get my lights lighting up, with a voltage where it was always 0 and the light never comes on at all, right? Obviously, those cases are different, and I ought to be able to express them differently. Plus, what if I had a different size AC voltage? What if I had an AC voltage that made bigger swings? Like, here's one that goes way, way, way up high, down through 0, way, way down low, down through 0. Well, what's going to happen is the average for that red curve, that's going to still be 0, right? Even though it goes up to a much larger V naught and a much larger negative V naught. It seems like the black line and the red line, I ought to be able to discuss them in a way that is different, because clearly there's something different about them. But if I just take a straight up average, I'm going to get 0 for both of them. So straight up averages aren't sufficient for talking about this kind of stuff. So the way that we're going to do this, the way we're going to manage to talk about alternating current, is we're going to take a special sort of average. And that special sort of average is called a root mean squared average. Or RMS. It's a special kind of averaging that you can use on these sort of repeating periodic sorts of functions that will average it in a way that takes into account that even when it's negative, it still matters. And the way you do it, well, it's kind of like this is instructions, except they're instructions written backwards. So here's the idea. We've got a voltage that looks something like this, right? Our voltage is some maximum voltage, V naught, times like a sine or a cosine of omega t, right? It's some kind of function that looks like a sine wave. Obviously, we can't average it now because we get 0. So here's what we do. First, we square both sides. I'm going to take this expression, I'm going to square everything. So on the left-hand side, I'm going to have my voltage at any given moment squared. I'm going to have whatever my maximum voltage is squared times the sine squared of omega t. As long as I do the same thing to both sides, the equation is still true. That still works. Now, if I square this function, then what's going to happen is if you take a negative number and square it, it becomes positive. So now what's going to happen is, instead of having a graph that looks like this, I'm instead going to have a graph it's going to be a little bit rounder. So it'll be like, but every time it goes to 0, 0 squared is still 0. But it can't go negative, because every time it starts to go negative up here, we're squaring it, it's going to pop back up and go positive again. So now I have a function that never, ever, ever goes negative. That's useful because now I can take the mean. I can take the average of this. Now, how am I going to get the average of this? Well, look at what it's made out of. I have a constant. Remember, V naught is just some number like 10. The average of a number is just itself. So if I take V squared average. It's going to be the average of this, which is just itself. But then I got to take the average of the sine squared. Well, how will I do that? Well, the biggest the sine squared could ever be is 1, right? The sine of anything can't go from higher than 1 or lower than -1. So the sine squared is going to go from 1 down to 0. Remember, it can't go negative because when it used to be, when the sine was -1, when I square it, it becomes +1. So what's going to happen is the sine squared goes from 0 to 1. If I take the average of it, it's going to spend just as much time above 1/2 as it does below 1/2. So the average of the sine squared is 1/2. That was easy. So I took the average of this over time and I get 1/2. So that was super easy. Now what's going to happen is, since I've taken the average while everything was positive like this, I want to go back to my original thing. I don't want the average of v squared. I want the average of v. So I'll just take the square root. So I'll say I squared it long enough to make everything positive, took the average while everything was positive, and then once I'm done with the average, I'll square root it to go back to my original units. So I got to square root this. So the average of v squared, or the square root of v squared average, is my average. The square root of this is just v naught, my original v naught. And the square root of 1/2 is the square root of 2 over 2. If that's not obvious, remember, if I do the square root of 1/2, we usually don't like to have radicals in the denominator. So sometimes you'll rationalize the denominator. If I multiply by the square root of 2 over the square root of 2, that's technically 1. It doesn't change the number at all. So I have 1 times 2 is 2. The square root of 2 times square root of 2 is regular 2. So that's what's happening there. And so this average is what we call VRMS, the RMS average of my voltage. And it's a number. And you can see how we're going to get it, right? We're going to get the RMS average by taking the peak voltage, that's the highest voltage we ever got up to, and multiplying that voltage by the square root of 2 over 2. Now, when you do the math, you'll find that this is a number. It's about 0.707. So if you're looking at a sine wave like this, the RMS average is 0.707, so it's about 70% of the peak. So it's not quite, it's a little bit more than halfway, but not quite 3/4 of the way up. So this would be my RMS voltage. If I know what the peak voltage is, I can find the RMS voltage. All I've got to do is multiply by 0.707. And that's it. That's the idea. And of course, we could do that for voltage, but we can also do that for other things. In an AC circuit, the current will also change with time, right? The current will have a similar mathematical relationship, so that when the voltage is big and positive, the current will also tend to be big and positive. So they'll tend to rise and fall in the same sort of way. So I could talk about the current RMS, and it would also just be the max current still times the square root of 2 over 2. And so if you know the max current, you can find the RMS current. If you know the RMS current, you can find the max current. And that's how that works. To give you a sense of like how that will play out in the real world, we know that in most American household circuits, the RMS voltage is about 120 volts. That's pretty standard. Now, if that's the RMS voltage, that's this 3/4 of the wave voltage. But that means that inside my walls right now, the current sometimes is bigger than 100, or the voltage, excuse me, is sometimes bigger than 120 volts. The peak voltage is a little bit larger. So if I wanted to find that, I know this is 120. I'm looking for this. So to get this, I would divide both sides by the square root of 2 over 2. So 120 divided by the square root of 2 over 2 is about 169. So at its maximum, the voltage across my prongs in the plugs in my house go as high as positive 169 and as low as negative 169, and they switch back and forth, back and forth, back and forth about 60 times every second. And so that's how we characterize alternating current. Now, in terms of what we're going to do with AC, that's basically it, right? That's literally all we have to deal with right now. We're going to revisit this concept later on in chapter 23. And in chapter 23, we're going to learn about some of the more complicated stuff that's going to happen when I take alternating current and I apply it to circuits that have things in them other than resistors, because they're going to behave in a surprising way. And we're not going to be able to understand that until we do magnetic fields in chapter 22. So everybody kind of clear on how that's going to play out? All right. I need to step away for just a second. Give me a second. I'm going to pause this recording. I hope. All right. So at this point, we pretty much finished off, the stuff from chapter 20. So chapter 20 is pretty well knocked out. Again, I'm pushing that due date until probably the end of the weekend. So you've got several days to do that stuff. But chapter 21 is going to really kind of it's going to be where you get most of the details about how circuits work. And what's happened was there were some principles that we've certainly ended up using in some of the problems we've done up until now, but we haven't actually given them names. We haven't really called them out. And so let's take the occasion to sort of formalize what those rules are, because for some problems, it's going to be super important to be able to use those rules, right? And the rules that we were referring to are called Kirchoff's rules.
And this is chapter 21.
It is chapter 21. Kirchoff's rules get sort of hinted at in chapter 20, but they get formally introduced in chapter 21. In actuality, we've been secretly using them since chapter 19. We just haven't been calling them this. So Kirchoff's rules are twofold, and they tell us about the behavior in literally any kind of circuit ever. Kirchoff's rules will always be true for every circuit ever. No matter how complicated, no matter what's in that circuit, whether it's AC or DC, they always work. And there are two of them. The first is called the loop rule, and the second is called the junction rule.
I remember a little bit of that.
Now, the loop rule is about voltage. It tells you about how voltages change in a circuit as you traverse any loop. And it says that the sum of all the voltage changes around any loop must equal 0. Now, what does that mean? Let's say that I've got some kind of circuit. Here's a battery. Here's a resistor. Here's a resistor. Here's a resistor. Here's a resistor. So in this circuit, I have several loops that I can travel through. All right, twice the Amaya right now. What's going on? All right, so if I go around this loop, if I start here and go around here, what's going to happen is the voltage is going to change several times. I'm going to go across this battery. If I go across that battery, the voltage is going to tend to go up by a certain amount, right? If this was a 10-volt battery, it would go up by 10 volts. However, when I cross this resistor, it takes energy to push myself through that resistor. The electrons face resistance going through that resistor, and as a consequence, the voltage or the energy per charge will drop as I go across there. So I had an increase of 10 volts going across this. That's like an energy boost for my electrons, but there's an energy decrease going across those. And when I go across this, there's an energy decrease again. And what the loop rule says is that the drops that I experience going across these two guys have to be the same as the increase of that, so that when I go around that loop and I have positive 10 minus something, it should equal 0. It's really a consequence of conservation of energy, right? If the loop rule wasn't true, if like the sum of all the voltage changes was, let's say, positive 2, then what would happen is an electron could just go around the loop many, many, many times, and every time it did, it would get more energy. Where's all that energy coming from? I don't know, but that electron could become super powered just by going around a bunch of times. But here, it gains energy here only so that it can spend energy here, and the total is always 0. If I went around a different loop, it would still have to be 0. So here I have 10 volts. I'm going to drop some. I'm going to drop some more. I'm going to drop some more. And now I'm back to 0. So going around the outside loop, these 3 voltage changes would have to add up to whatever the voltage increase was from that. That's what the loop rule tells me. So key point, loop rule is about the voltage. It's about how many volts I've got. Now, the junction rule is a little bit different, because the junction rule is not about voltage, it's about the current. And the voltage rule says that the current that goes into a junction, and by junction I mean an intersection, a place where the circuit splits. So like right here, there's a junction, because I could come in going this way, but there are 2 ways I could get out. And the junction rule says that the sum of the current into a junction must be equal to the sum of the current out. So here I have current coming in from the battery, and then it splits, and some comes out this way and some comes out this way. What the junction rule says is that these 2 currents that come out of the junction have to be the same together as what came in. And the junction rule is a consequence of conservation of charge. Because if the current is just how many electrons go past me every second, if I had 10 electrons go past me every second into the intersection, but only 8 of them came out, where'd the other 2 electrons go? Did they just vanish? That doesn't happen. The junction rule just says all the electrons have to go someplace. And so when you look at a junction, you should be able to account for all of them. Nothing should go missing at that intersection. So, I often think about circuits with an analogy. I kind of think about circuits where the charge carriers inside, the electrons, they're kind of like cars on a road, right? And so when I talk about the current, what I'm kind of talking about is the amount of traffic that I have, right? if you're measuring the current, you're counting how many electrons go past you every second, right? It's like counting how many cars go past. So this is just, the junction rule is just saying that none of the cars go into the intersection and then don't come out someplace else, right? Everybody comes in, comes out someplace. The loop rule is about voltage. And in my analogy, the voltage isn't about how many cars I've got. It's about energy per charge. So for the car, what would the energy be? That's like the amount of gas in your gas tank. So when the voltage is high, you've got a full tank of gas. And when the voltage gets low, your gas tank is empty. And so what that says is that in my analogy, all your cars, they leave the gas station with a full tank of gas. But according to the loop rule, they're always going to drive in just the right way that they'll use all their gas by the time they get back up to the station. So if I've got 10 volts of gas in this analogy, and I'm going through this direction, maybe I'm going to burn 7 volts of gas here and 3 volts of gas here, so that I'm back to 0 by the time we get back to there. But I could have gone another way. I could have burned 7 volts of gas here. But if I do that, I got to lose gas 2 more places. So maybe I've got 3 volts left, so I'm going to maybe drop 1.5 here and 1.5 here. Still, it's a total of 10. So no matter how complicated the circuit, no matter what path your electrons take, the total drops in voltage have to equal whatever voltage I started with. They always balance out to 0. Those are Kirchoff's rules. And we've been secretly using Kirchoff's rules for a while now. I'm going to mute whoever that was. So, back when we did the equivalent resistance rules and the equivalent capacitance rules, we were secretly using Kirchoff's rules, because how did we motivate some of those rules? Well, if I had 2 resistors in series, we made some assumptions about those, right? We said for those 2 resistors in series that V total had to equal V1 plus V2. All we're saying there is that the increase we got from this had to equal to the 2 drops there. That's the loop rule. So when we wrote that expression and used that to derive the equivalent resistance relationship, we were secretly using the loop rule the entire time. We also said that in this circuit here, when I had 2 things in series, the current coming out, I total, had to equal I1 and also had to equal I2. Well, we were kind of using the junction rule for that, because in this circuit, there aren't any junctions, right? So what that means is that if I have I total come out, if I have 10 amps come out of the battery, that full 10 amps had to go through this, and there's no place else for it to go. So that same 10 amps had to go through this as well. So the current had to be the same everywhere. And that was the second assumption that we had to make when we derived the equivalent resistance rules, right? When we did the same thing with parallel, right? Well, there we said that V total had to be the same as V1. Why is that? Because here's V total. If I go around this loop, the only resistor I go across is resistor 1. So this drop had to be the same as that increase according to the loop rule. That was true. If I went around the outside loop, though, I'd only have 1 drop there. So V2 had to be the same thing as well, right? That was the assumption. We also said that, I have here I total coming out, but I had I1 come out there and I2 come out there. And we said at the time that these 2 currents had to add up to that. So we've been secretly using these sorts of relationships the entire time. It's not really anything new. We just haven't put a formal name to it before. But it's going to be important that we do that, because if we don't put a formal name to it, there's going to be some problems that are just going to be too complicated for us to solve. But by knowing Kirchoff's rules, everything is solvable. And I want to talk about what sort of problems you'd be looking at to where you'd have to use Kirchoff's rules in order to solve them. And probably the big sort of the big tip-off that Kirchoff's rules are something you're going to have to use in their raw form is when the circuit is just too complicated to comprehend. That'll happen a lot of times when I've got multiple batteries. Right? Imagine I have a circuit like this. Here's a resistor. Here's a resistor. Here's another battery. Here's a resistor. Here's another battery. So a circuit like this would be a nightmare to try to use the equivalent resistance rules for. And the reason it would be hard is because if I only had one battery in this circuit, if these guys weren't here, then what would happen is I would obviously have current come out of this battery. It would come out here. It would get to this intersection. It would split and go this way and go this way and then back around. But if I only had one battery and it was this guy, if I had this as the only battery and these guys weren't here, then current would for sure come out of there, split going this way and around, or split going this way and around, right? If I only had this battery but not these two, current would come out this way, go this way around, this way around. But with all three of them, it's hard to know, is the current going to come out of this battery and into this one, or is it going to come out of this battery and into that one? I don't know, right? It's not obvious what's going to happen. And in order for us to solve the problem of what is going to happen, we're going to have to approach it a different sort of way. Having all these batteries in here makes it difficult for me to combine these resistors using series and parallel rules, because those rules aren't going to work quite the same way. So in order to solve this problem, I have to use a different technique. The minute I saw these multiple batteries in one circuit, I knew that my technique was going to have to change. And on the downside, the technique we're about to learn is undoubtedly way more complicated. It's going to be a pain. Algebraically, it's a mess. But here's the good news. Conceptually, it's ridiculously easy. There's a procedure. Just follow the stupid procedure and you'll get there, right? So here's how this is going to work. I'm going to call this guy EMF 1, EMF 2, EMF 3. I'm going to call this resistor 1, resistor 2, resistor 3. So what we're going to do to solve this problem is, because of the ambiguity about which direction the current is, we don't even know what currents we're going to have. So the first thing we're going to do is we're going to look at this circuit and we're going to make a guess about the currents. And here's the thing. We're not going to think about this too long and hard, because it literally does not matter what we guess. If we guess wrong, it's no big deal, right? It's going to get the same answer at the end anyway. So all we need to do right now is just make a guess for calculation purposes. Now, when we're going to guess the current, we're going to do it a little differently than we've been doing it. Because when we were drawing things up here, right, here I said, oh, this is I1 and I2, and I gave them different names, right? But that was kind of stupid, because in this circuit here, I1 had to be the same as I2. So why did I give them two different names? Why did I call them I1 and I2 when they're both the same number? So what we'll do instead of having I1 necessarily being the current through this one and I2 necessarily being the current through this one, instead what we're going to do is we're going to look to see where will the current in this circuit get changed? Where will it alter itself? And what's going to help me with this is that I know the current can only change at a junction, at an intersection. So for instance, if I look right here at this intersection, right, I'm going to have a certain amount of current that could come out of this intersection. And I'm just going to guess, maybe correctly, we don't know. I'm going to guess that maybe the current's going to come out of this intersection going this direction, right? Now, if it comes out of the intersection going this direction, it's going to go around that bend, through that battery, around this bend. So it's going to go up around here. But there's no intersections between here and here. So all around this bend, whatever current I have here has to be the same as what I have here. It can't change in between. So I'm just going to call whatever that current is I1. And I'm going to assume, maybe correctly, I don't know, that that current is flowing clockwise, right? I could be wrong. It could be going counterclockwise. It doesn't matter. I'm not going to worry about it too much. But I'm going to call that current I1. Now, what about other currents?
What was your start point?
What's that? So when I'm identifying my currents, I always start at an intersection and then go until I get to another intersection.
Okay.
So I started right here. I went around. Remember, that's not an intersection. It's just a corner.
Mm-hmm.
I went around and didn't stop until I got to there. Does that make sense?
Yes.
So that's my first guess. I'm going to guess that that current is I1. Now, what about if I went from this intersection straight down the middle until I got to that intersection, right? What if I went straight down through here? I'll call that current I2, and I'm going to assume that I2 travels downward. Again, it could be upward. I don't know. All right, what about if I started here and went around this way? Let's call that I3. So far, so good?
Yes.
So all we did was we made some guesses. And at this point, you'll notice there's no more guesses to make. I went from every intersection to every other intersection. And I ended up with 3 different currents. So what that means is that I'm going to have enough equations to solve for all 3 of those currents. So even if I give you numbers for all the EMFs and all the resistances, I'm still going to be solving for 3 I's. That means I'm going to have at least 3 equations. Now, once I have guessed the currents, the next step is I'm going to generate those 3 equations that I need by using the loop rule and the junction rule. First, I'm going to generate equations with the loop rule. Now, the loop rule says the sum of all the voltage changes around any loop must always equal 0. So I'm going to start going around loops and just tallying up all the changes in voltage that I get as I go around that loop. Now, if I'm going around a loop and I cross a battery, the voltage will change by whatever the EMF of that battery is. So if I'm going around this loop here and I go across this battery, it's got a voltage of EMF 1. Let's say that's 10 volts. Now, if I'm going around that loop clockwise, I'm going from the negative terminal of that battery to the positive terminal of that battery. That would be an increase of 10 volts. But it's just as likely, if I'm going around a loop, that maybe I go across a battery from the positive terminal and I end up at the negative terminal. I'm going across the battery, but backwards. If that's the case, the voltage was higher where I started and it was lower where I finished. So if I'm going for batteries, if I'm going from the minus to the plus terminal, in other words, from the short side to the long side, that's going to be a plus EMF. But if I'm going across that battery backwards, I'm going to treat that battery like a voltage drop rather than a voltage increase. Does that make sense?
Yes.
So for when I'm tallying up my voltage changes, every time I cross a battery, I'm going to apply one of these two rules. Now, what about for a resistor? Well, for resistors, we use Ohm's law, and Ohm's law says that delta V equals I times R, right? So the voltage change across that resistor is going to be whatever current goes through that resistor times however big that resistor is. Problem. Normally in a DC circuit, your current is going across the resistor, and it starts off at a high voltage, and it loses energy as it goes through the resistor, so that it comes out with a lower voltage than it started. But what if I'm going around my loop one direction, but the current is going around the loop some different direction? So like if I'm going around this loop and I'm going the same direction as current one, and I cross resistor one, I'm coming in on the high voltage side, but I'll be coming out on the low voltage side. That would be a voltage drop. So if I'm traveling with the current, it'll be a voltage drop. So the voltage change, if I'm going with the current, sorry, guys, it'll be negative whatever the current is times R. But if I end up going against the current, if I'm going against the current, it would be a voltage increase. And this is why we had to make a guess about the direction of all the currents, is because by making that guess, we could then know whether to make all those IRs positive or negative as we develop our loop rule equations. And again, it doesn't matter whether we guess correctly or not. What's going to happen, though, is by making that guess, we're going to keep ourselves consistent so that somebody else who made a different guess about the direction of the currents, they may end up with different looking equations, but all the things that they have positive, we might have negative, but all the things they have negative, we'll have positive. It'll be appropriate. If we didn't make a guess about the currents, there would be some inconsistency. And that would be unfortunate. That would cause problems. So we're going to use the loop rule. We're going to generate some equations. And we're going to keep generating equations up until we've gone through loops that contain every element of the circuit. So stop when you've gone through everything, at least once. So once I've gone through all the resistors and all the batteries in the circuit, doing additional loops won't tell me anything that I don't already know. It's just going to be redundant. So the third step is use the junction rule. And we're going to use the junction rule until we get enough equations to solve. At step 4, do the math. So that's going to be the process that we'll use for solving a problem like this. Is we'll guess the currents, we'll generate some loop rule equations until we run out of loops to do. Once we do that, we'll use the junction rule until we have enough equations to solve it. In this case, we're going to need 3. And then once we have the 3 equations, we do the math. So for this example up here, I've already made my guesses. let's start generating some equations. So I'm going to pick some spot on the circuit, and it doesn't matter where I start. Just pick a place and then go around the loop until you get back to that place. I like to start at intersections, but it doesn't matter. So I'm going to start right here. I'm going to go around this loop, and I'm going to go around that loop clockwise. So nothing, 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 nothing. Okay, now I'm crossing battery 1. I'm going from the negative terminal to the positive terminal. So it's a plus. So it's positive EMF 1. Now I'm going to go across resistor 1. Now I'm going with the current. So with the current is negative. So it'll be negative. Well, which current is it? Right now it's I1 in this section. So I1 times R1. Now I got to go back down this way. So I'm going across resistor. Did I label that resistor? I did not. I hereby christen you resistor 4. So here I'm going across resistor 4. So I'm going with the current. So it's negative. So minus, but it's current to resistor 4. So minus I2 times R4. Cool. Now I'm going across a battery, but I'm going from the long line towards the small line. That's backwards across the battery. So from the plus to the minus. So I'm going to treat this like another voltage drop. So it's minus EMF 2. But now I'm back to where I began. So all of these voltage changes that I just tracked have to equal 0. That's the loop rule. Everybody cool on where that equation came from?
Yes.
So now I'll do another loop. So I'm going to pick a spot. It could be the same spot I started before or a different spot. It doesn't matter. I'm going to go around a different loop. So before I went around this loop, let's do this. I'm going to start here, but this time I'm going to go clockwise around this loop right here.
Okay.
Again, it doesn't matter what loops you pick. I could instead go around the outside. That would have worked. Any loops you choose are fine. Just to make my life easier, I like to, when I have a choice, make my loops as small as I can make them. That tends to make my equations shorter, which makes the math easier. But it doesn't matter. You get the same answer no matter what. So don't think too hard about it. So I'm going to start here. I'm going across battery 2. I'm going this time from the negative to the positive terminal. So this will be a plus. So plus EMF 2. Now I'm going across resistor 4 again, but this time I'm going upstream because the current was downward, but I'm traveling upward. So it'll be plus I2 times R4. Now I'm going to go across resistor 2. Notice the current I have go through resistor 2 is going around counterclockwise, but I'm going clockwise. So plus I3 times R2. So far, so good?
Yes.
Then I'm going across battery 3 from the positive to the negative. So minus EMF 3. Then I'm going across resistor 3, still going against the current. So it's plus I3 R3. And all that equals 0. Because now I'm back to where I started. So at this point, I've done 2 loops, but I've gone through all the resistors and all the batteries at least one time. So even though I could, in principle, go around the outside edge, and that would be a different loop, it's not going to get me an equation that tells me anything new. If I go around the outside loop, what I would end up getting is the algebraic combination of this guy and this guy. It wouldn't help. So I still need 3 equations, though, because I'm going to have 1 equation for every unknown, and I have 3 currents. So the last equation is going to come from the junction rule. And the junction rule says the current coming into a junction has to equal the current coming out of a junction. So here's a junction. There's two of them. I could have picked this one here. It doesn't matter which one I pick. I'm picking the bottom one. And if I look at what current comes into that junction, the arrow for I2 is coming in, but the arrows for I1 and I3 are both coming out. So here, I2 is the current coming in, and I1 plus I3 must be coming out. So once I have gotten those three equations, I'm good to go, right? At this point, all I've got to do is solve those equations for the three currents. So that's the process. And here's the thing, right? Solving three equations simultaneously, kind of a pain in the butt. All right, algebraically, it's not fun. But let's say this was an exam question and you suck at algebra, right? What I've seen many students do in the past, and I've found myself grading exams and just like screaming, why? At my students, because they'll see this problem and be like, man, that's really hard, skip. And they just leave it completely blank. And I'm like, no. Because yeah, even though this problem is kind of hard, this process is super easy, right? If I saw this on an exam, right, what I would do is I would generate those three equations, right? This is the part where it stops being a physics problem, becomes a math problem. I would get the points for finding those equations. If I'm grading that, that's like 14 out of 20 points just for getting here. Now, those last 6 points, those are going to be a really rough 6 points to earn. What I would probably do if I was a test taker is I'd move on, do the rest of the test, and I might come back and give a crack at it, like if I have extra time at the end. But man, I'm going to lock up those 14 points right off the bat because, man, that's low-hanging fruit. So just because the question is hard doesn't mean you can't at least set it up. The setup is easy. The setup is super easy. And that's what I would expect of you. So how do I solve all this garbage? All right. I've got this stuff. How the heck am I supposed to solve three equations and three unknowns? Now, just to make things clear, I didn't actually specify any numbers. But
one was equal to 10.
yeah, what's going to happen is, let's assume that for this circuit, I know all the EMFs. So EMF 1, EMF 2, EMF 3, those are just some kind of numbers. And R1, R2, R3, R4, those are numbers. I know all those numbers. So even though this looks complicated, most of these are just numbers I'm going to fill in here in a minute. Right? The unknowns, the variables are the currents. Now you'll notice in each of those three equations, like in this first equation, I have two variables. There's two unknowns, can't solve it. This one here, well, there's still two variables. There's I2 and then I3 appears twice. And then this one here, all three are unknown. That sucks. But I can still solve this problem by being clever. So here's what I would do. First, what I would do is I would take some of these guys and I'd pretty them up a little bit. Like, for instance, this guy right here has I3 appear twice. If I had an equation in algebra class that had 5x plus 2x, well, I'm going to combine like terms, and 5x plus 2x would turn into 7x. We're going to do the same thing here. I have something times I3 plus something times I3. I'm going to combine like terms and get something plus something times I3. So I'm going to rewrite that second equation as EMF2 plus I2 R4 minus EMF3 plus I3 times R2 plus R3. I'm just taking this term and this term, factoring out the I3s to get them together. So far, so good?
Yes. Yes.
All right. Now, this is just equation 2 rewritten. Now, the thing that I notice is that equation 1, this first equation, it has current 1 in it and current 2 in it. This equation here, though, has current 2 in it and current 3 in it. So what's happening is I love to combine this equation with this equation. And the easiest way to do that is with like some kind of substitution. But the problem is if I replace, let's say I solve this for I2, and I plug I2 in to that equation up there. Well, now I2 won't appear in that equation anymore. Unfortunately, what would happen is I'd be replacing I2 with something that had I3 in it, so it wouldn't really gain me any additional ground. So that's kind of sucky. However, what I can do is what if I take this equation, and here I notice that according to this third equation, I2 is equal to I1 plus I3. So what if I did this? What if I replaced the I2 in this first equation? I2 no longer appears. I'd be replacing I2 with I1, which we already had in that equation. That's cool. Plus I3, which we have in that equation.
It's not in there.
No, sorry. Let's take I2 not in this equation. Let's replace I2 in this equation. Because then I'll have... No, don't need that way either. I guess I'm going to have to rearrange it. Because the oddball out is not I2, it's I3. I3 appears here, but nowhere else. So, instead, let's do this. Let's get rid of I3. If I replace I3, I can replace it with I1 and 2. Then I'll have 1s and 2s everywhere, and I can combine them. So let's do it that way. Now, according to this, I2 equals I1 plus I3, but that implies that I3
is going to equal I1 minus I2.
Other way around.
Oh, really?
Well, look, I want to get I3 by itself, right?
Yeah.
I'm going to subtract I1 from both sides. So it'll be I2 minus I1.
Got it.
You got to be super careful with your minus signs. It will mess you up. So far, so good?
Mm-hmm.
So let's take I3 and make it be this. Let's plug this expression into that equation. So now I'm going to have EMF2, that's the same, plus I2 R4, the minus EMF3, that's the same. Now it's going to be plus, and I'm going to have I2 minus I1 times R2 plus R3. So I just swapped out I3 with what I knew I3 had to equal. Now, this is ugly. Let's pretty that up a little bit. First thing I'm going to do is I'm going to FOIL this out. So I'm going to have EMF2 plus I2 R4 minus EMF3. That's a 3. Now, when I FOIL this out, it's going to be this times this. So it's plus I2 times R2. Then it's going to be this times this. So plus I2 times R3, right? Then it's going to be this times this. So minus I1 times R2. Then this times this. So minus I1 times R3. Now, let's combine like terms. I've got I2s here, here, and here. They're all pluses. So I'm just going to factor out the I2. So I'm going to have, let's get all things that don't have I's. So I have EMF2 minus EMF3. Then I'm going to have plus I2 times R4 plus R2 plus R3. So far, so good.
Mm-hmm.
Then for the I1 terms, I have two of them. They both have a minus I1. So I'm going to factor a minus I1 out of both of those. And it's going to leave behind R2 plus R3. So now what I have, by combining equations 2 and 3 and just prettying them up a little bit with algebra, is I've got an equation that's got I2 and I1 in it. Now, up here, this very first equation, we haven't used that yet. That's the other one that we haven't used, but it also has I1s and I2s in it. And so if I use one of those equations to eliminate I1 or I2 from the other equation, we're good to go. Now, it looks complicated because I have a bunch of stupid letters here, but you know how to do this process because you learned it in algebra back in the day, right? You've solved plenty of problems in your day where you had something like 3x plus 2y equals, I don't know, 5, and 5x minus 3y equals 7, right? If this was algebra class and you were solving that problem, how would you do it? How would you solve for x and y? Any ideas?
You said how we solve for X and Y?
Yeah. I'm trying to show you that the thing we need to solve this disgusting, ugly set of problems is exactly a thing you've done before, but it just probably looked different when you were in algebra class.
Don't you do no, never mind. I was about to say like terms or common denominator or something like that.
No, nothing like that. There's two ways to do it. One is the substitution method, right? I could pick one of these equations and pick one of those variables and solve for it. Like I could get y by itself and then plug in for y there, and then I'd have nothing but x's. So that could work, but it's kind of a pain. There's another method that we learned back in the day called the elimination method. And that's going to make our lives super easy. Here's something I noticed. Notice how I have this y term is positive, but this one over here is negative.
Mm-hmm.
If I could manipulate the equations just right, so that if I added the two equations together, I had positive something y, and then over the other one I had negative the same thing y, the two y's, when I add them together, would cancel out, and they'd be gone. Now, right now, it's not going to do that because 2y is not going to cancel out negative 3y. But if I'm clever, I can make them cancel. Here's the trick. I'm going to take this top equation. I'm going to multiply everything on both sides of this top equation by whatever y was multiplied by in this equation. So here, I'm going to multiply everything in the top equation by 3. So I'll have 3 times 3x is 9x. 3 times 2y is plus 6y. 3 times 5 is 15. I just tripled everything. Meanwhile, in this second equation, I'm going to do the same trick, except I'm going to multiply everything in that second equation by whatever y was multiplied by up here, which is 2. I'm going to double all this stuff. So 2 times 5x is 10x. 2 times 3y is negative 6y. Oh, look at that. That's awesome. 2 times this is 14. So both of these equations have to be true because I just took these and multiplied them by the same things on each side. But by being clever about what I picked, now if I add these two equations together, well, this plus this is 19x. This plus this is 0. This plus this is 29. So therefore, x equals 29 over 19. And if I then take that expression and plug that back into here, I can now solve for y. That's the trick that you've learned how to do in algebra, and it's still going to work here. But look what we've got here. It's a little bit messier, right? Now what I've got is I've got this is like my x, this is like my y. I got garbage times x, different garbage times y. Up here, I've got, remember, this is like my y, that was like my x. So I've still got garbage times x, garbage times y. I'm going to do the same trick, right? Let's get rid of, let's see here. I1 is negative both places, but I2 is positive here and negative here. So let's do this. Let's do the same trick that we did a second ago. We're going to add the two equations together and make everything that's not what we want cancel. So that means for this equation, I want to make the coefficient of I2 be the same as the coefficient of I2 from the other guy. And that means I'm going to multiply everything in this equation by whatever I2 is multiplied by up here, which in this case is R4. So everything in this equation, I'm going to multiply it by R4. So, yeah, remember, R4 is just a number, right? It's just like when we were here, we said, aha, I'm going to take everything in this equation multiplied by 3, right? R4 is like the 3. So, EMF2, nope, it's EMF2 times R4, whatever the heck that is. EMF3, nope, it's EMF3 times R4. This garbage here, nope, it's plus I2. I'm going to multiply by R4, and I'm still multiplied by all this garbage. All right. This guy here, I'm just going to multiply by R4. And of course, 0 times R4, still 0. Boy, that's ugly, but apparently it's still true. That was easy. Now, what about this other equation? The one we haven't ever done anything with this one. Well, for this one, I'm going to multiply everything in this equation by whatever I2 is multiplied by in this equation, which here it was multiplied by R4 plus R2 plus R3. I'm going to multiply everything in that first equation by this. Right? And you might be thinking, man, this is a freaking nightmare. It's not that bad. I'm going to have EMF1 times R4 plus R2 plus R3, whatever the heck that number is. I'm going to have negative I1 R1 times R4 plus R2 plus R3. Okay, whatever. I'm going to have minus I2 R4 times R4 plus R2 plus R3. And then minus EMF, is that 2? Minus EMF2. R2 plus R4 plus R3 equals 0. It still equals 0. Ran out of room there. Whew, that was a mess.
Oh my goodness.
Except look, now I've got this equation and this equation. I'm going to add them together. And what's going to happen is when I add them together, I'm going to have this term right here has I2 R4 times all this garbage. Over here, I have I2 R4 times this garbage, but it's negative. This term and this term cancel out. They're going to take the I2s out with it. Now, what's going to be left is I'm going to have all this, 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 and this, but the only variables in any of that garbage is I1. Whew. So we have EMF2 times R4 minus EMF3 times R4 minus current 1 times R4 plus R2 plus R3. That's this. Now I got this guy. So plus EMF1 times R4 plus R2 plus R3 minus this garbage. I'm going to continue it down here. This, so minus EMF2 R2 plus R4 plus R3. So this looks terrible, right? This looks terrible, but it's not that bad. Because remember, this, those are just numbers. The only variables are this and this. So when I go to get them by themselves, all I got to do is take all the variable stuff, move it to one side of the equation, and leave all the constants on the other side. So it looks kind of hideous.
Wait.
No, I'm just going to move it up out of the way. I'm trying to keep it on screen.
Yeah, I need the bottom part.
Right. So all I'm doing is I'm moving this term and this term to the other side. So all the other stuff I'm going to have EMF2 R4 minus EMF3 R4 plus EMF1 R4 plus R2 plus R3. I have this term over here, so minus EMF2 R2 plus R4 plus R3. And all that equals, on the other side of the equal sign, I have positive this and positive this. So that's I1, R1, R4 plus R2 plus R3 plus I1, R4, R4 plus R2 plus R3. Yeah. Now, I got I1 times garbage plus I1 times garbage. Factor out the I1s. It's going to equal I1 times this garbage plus this garbage. So I'm not going to write all this over again. I'm going to have ditto equals, and then I'm going to have I1 times this plus this. And then I have one last step to be done with I1. I'm just going to divide both sides by all of this garbage. So at the very end of this, I'm going to have I1 by itself. It's going to equal this, which is this stuff. So EMF2 R4 minus EMF3 R4 plus EMF1 R4 plus R2 plus R3 minus EMF2 times R2 plus R4 plus R3. All of that over R1 times R4 plus R2 plus R3 plus R4 times R4 again plus R2 plus R3. Right. That's a nightmare. But at the end of the day, I can just plug a bunch of numbers in, and I now have a number for I1. Head explodes, right? Except here's the cool part. Once I plug in and get a number for I1, what do I do with that? Well, let's go back to my original equations for a second. In my original equations, I had this, here's I1, which we now have a number for. Here's I2. If I know what I1 is, I can just solve for I2, right? It's not even that hard. I'm just going to move this to the other side, divide by R4. So I2 is going to end up equaling EMF1 minus I1, which we now know, times R1 minus EMF2 divided by R4. So it was a nightmare to get I1, but once we get it, getting I2 is pretty easy. And heck, I3 is super easy. I3 is going to equal I2 minus I1. No problem.
A lot.
So once we plug in our numbers, we're good to go there. Super easy. Now, here's what's going to happen. You'll notice that in several of these terms, like here, this has got a plus sign, but that's got a minus sign, right? So this could be negative. This could be negative. And what could happen is it's entirely possible, depending on what the numbers are for some of these things, that I1 or I2 or even I3 might turn out to be a negative number. And you might think, well, what would it mean if I have a negative number for my current? Well, let's say that we plug in all our numbers and we end up getting a negative number for I1. What would that tell me? Well, when I made these equations up, we made some guesses about the currents. And we guessed that the current was going around clockwise. If I solve the problem and I end up getting a positive answer for I1, that would tell me that my guess was correct. If you get a positive value for the current, it means that whatever direction you guessed in your first step, you had guessed correctly. However, if you get a negative answer for the current, all that tells you is that when you went back in your first step, if I got a negative value for I1 at the end, that would tell me that no, I guessed that it was clockwise, but apparently it was the other direction. It was counterclockwise. So the sign of your answer just tells you whether or not the guess you had originally was correct or not. And even if you had guessed wrong, the magnitude of your answer won't change. So like if the current was supposed to be 2 amps clockwise, right? Then what's going to happen is I would get positive 2 for current 1. Had I guessed wrong, I would have gotten negative 2. But either way, it would have been a 2, right? It wouldn't have been like negative 5. It's going to be the absolute value of your current is going to be the right answer. And the direction you can figure out based on whether your answer is positive or negative. And that's going to be true for all of these silly Kirchoff's law problems.
Okay.
So is it complicated? It can be.
You said if my answer is negative, that means I need to go back and.
It just means that when you go back to look at what direction your answer was, it's the opposite direction of what you originally guessed.
Basically turning it to absolute value with no negative, right?
Right. So if I plug in my numbers and I get I1 equals negative 2, right? If this turned out to be negative 2, what I would say is, aha, I1 is 2 amps, but the direction is not this direction, it's this direction instead.
Okay.
And that's it. That's the whole deal. So are these things complicated? Yeah, they're complicated. Are they impossible? No, they're not impossible. And bear in mind, this one looks a lot worse than it was because I was trying to maintain like genericism the entire way through. You can always just plug the numbers in and it makes it a little bit less frustrating for you. But that's the concept. That's the process. How are we feeling about that? We can do those in our sleep?
Yeah, I was just gonna, you gotta take your time and do it.
You do. You have to be very, very careful. It's super easy to drop minus signs. So be careful when you're doing things like distributing through and combining like terms. Make sure you don't drop a minus sign. that'll mess you up. But other than that, they're pretty straightforward. And there's a couple problems on your homework where you have to do this process. Now, what can happen is I can make the circuits way, way more complicated than this, right? Here, I only had 3 currents. But what if I had instead been a jerk? Because you know I like to be a jerk. What if I'd given you something super crazy? Like, here's a battery, here's a resistor, here's a resistor, here's another battery, why not? Battery, resistor, battery. Resistor.
Oh my gosh, Dr. Fleming.
All right. Now, how many equations would I have to solve this problem?
5.
More than that. So I would do the same process, right?
Okay, hold on.
The first thing I would do is I would guess my currents, and the currents are going to go from any intersection to any other intersection. So like here's an intersection. From here to here, let's call that I1, right? From here to here, we'll call that I2. And I'm guessing a direction each time. From here to here, I3. From here to here, I4. From here to here, I5. From here to here, I6. There to there, I7. There to there, I8. There to there, I9. There to there, I10. And from here to here, I11. So in order for me to solve this problem, I'd have to have 11 different equations, right? Am I ever going to make you solve 11 equations and 11 unknowns? Heck no.
Please.
I don't want to solve this problem. This problem is too disgusting for me to want to even think about. However, what I would be willing to do is to make you write the equations down, right? Could you write the set of 11 equations that could be solved for this? Heck yes. That wouldn't even be that hard. So no matter how complicated I make it, writing the equations is easy. That's the physics part. The math may be really, really nasty, and I wouldn't want to have to solve 11 simultaneous equations if I didn't have to. But you could. Does that make sense?
Yes.
All right. All right. I will let you guys go till tomorrow. Have a good day. Tomorrow we will tackle RC circuits.
Okay. I'm gonna email you. I'll probably be dang, I was drawing the picture, Dr. Fleming. But I probably
Oh, I'm sorry, I put it back.
You're fine. Look, we didn't solve anything. It's okay.
Yeah. I was just demonstrating that, you know, like how you would set up a problem like this.
Yeah.
And the point is that I can make them arbitrarily complicated. The first step is just guessing your currents, and you can do that for ridiculously complicated circuits.
Okay. Probably be using office hours today because I know that we have a test. Oh, and my question was, will we be able to, like, I know you said it'll be due like Friday. Will we be able to go like back and forth, like start it but like close it, or?
No. Unfortunately, you're going to have to set aside a 2-hour block because once you start it, it's going to run itself out. You won't be able to walk away without the timer expiring for you.
Okay.
So, because otherwise what would happen is people would just open it up, look at the questions, close it, work it offline, come back.
Yeah.
You know, if the clock was only running when you had it open,
Yeah.
it would be super easy to circumvent. So I can't have you do that.
Okay. And how many Up to like how many questions do you think?
I haven't finished writing it yet, so I don't know the answer to that. My guess is probably something like 8. It seems like a lot, but bear in mind that a lot of times some of those 8 questions might be like a part A and a part B.
Yeah.
So that's a scenario, and you'll all have like there'll be different versions of the exam, so you won't even have the same questions as somebody else necessarily. But that's how that'll play out. They'll probably somewhere in the neighborhood of 8. That's where I settled last time. Some of them will be open-ended in an effort to get you guys to sort of think conceptually. But that's what you'll expect.
Okay.
All right.
Have a great day.
You too.
Talk to you later.
Yes, ma'am.